Am I audible now?
Yes, you are audible, sir.
Yeah, so yeah, welcome to the tutorial, the third session of the materials characterization course. And so in the last class, what we have gone through is that we have covered one mode of different modes of the optical microscopy, light optical microscopy, that is the bright field microscopy as well as the dark field microscopy. And then we covered two different kind of microscopy as well, that is phase contrast microscopy, and this the another thing we covered, that was the polarization microscopy. So here we'll see there are the last two variation of the microscopy, the light optical microscopy. That thing is called as differential interference microscopy. So this is another mode of microscopy where, what this does, the imaging system in the differential interference microscope. As earlier we have known that in phase contrast what happens. So in phase contrast, so the basic idea of the phase contrast was the optical path length, it was converted to phase difference, right? So this was the basic idea of the phase contrast microscopy, that the optical path length was converted to phase difference, and subsequently from phase difference the amplitude difference was created, and then we were getting contrast. So that was given the name as phase contrast microscopy. But here what we will do in here also we will create an imaging system in such a way that we will be able to see the phase difference in our specimen, but we will not directly interpret the optical path length as our contrast difference. What we will do, if let's say in our system, in our object, there is a gradient in the optical path length exists. Last time I told that the optical path length, if anyone remembers the optical path length formula, that is n into t, where n is the refractive index and t is the thickness of the medium. So if there is so this corresponds to a single value. But let's say for a material and for a different for a system, there are the gradient in the optical path length exists. It might not be very huge, but still let's say there is a gradient in the optical path length exists. Then how? Because in phase contrast microscopy we will not be able to get that contrast in our image. So how we will see in that case the contrast, we will see through a method called differential interference microscopy. And this differential interference microscopy is an imaging system that converts the gradients in optical path length. So not only the optical path lengths, but the gradients in the optical path length. So how will we see the gradients in the optical path length? That we will see in the subsequent slides. But this to see this gradient in the optical path length, when we put our object in under the microscope, then there is a relief like structure or a shadow cast appearance. If you are not able to visualize a shadow cast appearance, in simple terms we call it as a like a deceptive three-dimensional appearance. Means that our image is formed in two-dimensional, but we will get some of the images in such a figure, in such a way that we will think that okay, this is a three-dimensional appearance in our. So this is a two-dimensional figure image we will get. Always we are getting a two-dimensional image, but the two-dimensional image will we will be interpreting this two-dimensional image as a three-dimensional image. That means the material might not be means it might not be giving the true three-dimensional features, but we will be interpreting as a three-dimensional image. Okay, so that will be a relief like or a shadow cast appearance. And generally the cells or you can say the biological samples, they are viewed through this differential interference microscopy. Okay, and how we use this differential interference microscopy? So we use a method called dual beam interference optics. So that means there are two different kind of beams we incident we would like that our specimen should interact with, and out of the interaction from the for out of the interaction with these two different beams, we will get some kind of contrast, and those contrast when we put it see, then that is called as interference, and those contrast when we see in our under the microscope, then that is called as differential interference microscopy. And what does this dual beam interference optics, the different component? So one of the major component of this dual beam interference optics is that the light should be a polarized one. So last class we have gone through the polarization microscopy. Similarly, the polarized light means, let's say my E vector or the electric vector is going in all such direction. This is my E vector. So if I keep a polarizer in such a way that my this is a polarizer, let's say, so this E vector will only this E vector is in all such direction. But if I keep a polarized the polarizer in such a way that the E vector only in this direction will be allowed to pass, right? So from randomly polarized, so this thing we have studied in our previous class. So this is in randomly polarized, this is a linearly polarized. Similarly also, if I want, instead of linearly polarized, I can also get some elliptically polarized or circularly polarized, different kind of polarized light I will get. So that is one of the major component of differential interference microscopy. And there are other additional features. This is polarized microscopy we have already seen in the previous microscopy. So what is the additional feature that we will integrate in differential interference microscopy? That is called as Wollaston prisms. Okay, and these Wollaston prisms are used in two numbers, right? That is called Wollaston prism 1 and another one is called Wollaston prism 2. So one is called as standard Wollaston prism and the one is called as modified Wollaston prism. We'll see why they call that. And modified Wollaston prism, or sometimes they are also called as Nomarsky prism. So this is Wollaston prism and this is Nomarsky prism. Okay, so this is the basic idea of our differential interference microscopy. That means the local gradients. Yeah, so this is the optical system and the basic idea of our DIC microscopy. That is it is a dual beam interference mode that we are using, and the local gradient in optical path length to regions of contrast we are using. So the gradient in optical path length, so as I said, the optical path length is n into t. Here n is the refractive index and t is the thickness. Okay, so local gradient in optical path length to regions of contrast, this optical system is converting that thing. So that is why this is known as differential interference microscopy. And we know that optical path length between 2 points is a function of transit time, how much time it takes, and the number of cycle of vibration. If you remember last class, I have drawn some wave like this and wave like this, and I have told that though the geometrical distance between, let's say this is point A and point B, and this is wave 1, wave 2, though the geometrical distance traversed by the wave 1 and wave 2 between point A and point B, and this is the length, are different, but the optical path length are same in this case. Okay, but we optical this path length is a so this is a function of number of cycle of vibration. So this optical path length is given by nt, and the number of cycle of vibration, that is given by nt by lambda, right? So that means if our wavelength varies, then number of vibrations will also, the number of cycle of vibration will also vary. So keeping these things in our mind, that optical path length can also vary based on the transit time, how much time it is taking through different mediums, right? And how many number of cycle of vibration it is going through. We designed a set of system which will give us, though the optical path length necessarily it need not be same, how to see the difference in contrast. In those cases we have designed the DIC microscopy. Okay, and So what is the difference between phase contrast and DIC? In phase contrast, what we are seeing? We are seeing optical path length to phase contrast. Directly we were seeing. Right? That was the motive for DIC microscope. The phase contrast microscopy. But in DIC, what we are doing? So here in this figure, if you see, let's say this is our this is one image, and this is the figure. So we know that the amplitude in DIC, like I said, this will be the name comes from differential interference microscopy. So the differential terms come that the derivative of the gradient means we are taking the derivative of the path length, optical path length. That is why the name come. This is what the differential means. Okay, so this is if you see, look at this image, then we are taking the optical path length traversed from here. So along this line, if you see, then this is the optical path length versus, so this image is the optical path length versus distance diagram. Here you can see the first optical path length, this when I am starting from this, you just consider this curve, I am starting a little down. So when I am going like this, then initially from here to here, my optical path length is not varying that much with respect to the distance. So that is why my optical path length is the gradient or the derivative of that optical path length, since it is constant, it is almost here 0, right? And when it starts to increasing up to a point, certain point, then you can see the variation in the optical path length from here to here. You can see it starts increasing. Okay, and then what happens again when it starts to decrease in this region? In this region, when it starts to decrease, it again starts to decrease. Then same thing happens. It at this point it becomes 0. Then again after this it starts to decrease up to this point. Then again it starts to decrease, and then comes a point here. It becomes 0 here. Then again it starts to increase. It starts to increase. So that means whatever the optical path length I am getting, I am doing nothing in differential interference microscopy. What I am doing, I am just taking the derivative of that optical path length. So that is why you can see, if I am I designed a detector which is able to capture the amplitude, and I design in such a way that the amplitude should be this one. The amplitude should not directly correlate with the optical path length. Rather, the amplitude should be correlated with the differential, the derivative of the optical path length. Then what will happen? Instead of getting a peak like this, I am getting a sharp peak, right? Instead of getting here, instead of getting a broad peak like this, like this, like this, and like this, I am getting a sharp peak. Okay, I am getting some peak like this. That means my amplitude now as compared to this curve, let's say this is curve, this is plot 1 and this is plot 2, as compared to plot 1, my plot 2 is showing much more in amplitude. So if amplitude increases, then intensity, if there is variation in amplitude, then similarly intensity will also vary. If intensity variation is large, then in that case what I will get? I will also get large contrast. So this is the idea behind phase contrast behind phase contrast microscopy versus the differential interference contrast. So what we do in differential interference microscopy, we generate two set of rays. Not how will we get the different, since if one ray is going, then the optical path traversed by that one ray will be same, but we want to see the gradient in the optical path. So that is why what we do in DIC, we split the ray into two set of ray. One is, since I am using polarized, right, from previous tutorial you might have remembered, one is ordinary ray and another one is extraordinary ray. So to generate this ordinary ray and extraordinary ray, I need some kind of instrument that also I have to use in differential interference contrast microscopy. And so these ordinary ray and extraordinary ray are generated by a thing called beam splitter. Okay, that means the name suggests that it is splitting a beam into two different parts. And the first we are splitting the beam by this beam splitter, Then same thing we are doing also. So this is we are splitting the beam from the object size. Then same to if we are splitting one beam into two different beams, then after refraction or after diffraction, then same two beams will also be present. But for the image formation, we need one beam. So again, after first we are splitting the beam, then after interference, let's say interference happen, then after interference again we are recombining the beam. And this, so splitting is done by one beam splitter and recombination of the beam is done by the second beam splitter. So this is what we are so this combination of entire this splitting and recombination, these are done by Wollaston prism. Okay, and why we need from Wollaston to modified Wollaston or the Nomarsky prism, I will tell, but this is the idea behind that. First we are splitting the beam so that we will be able to see, or we will be able to view the optical the gradient in the optical path length, and then we have to somehow recombine, because we cannot project, otherwise what will happen, the double refraction what we have seen in through calcite in previous class, that will take place, but that will not give us distinct features in our microscopic image. Okay, so this is the reason that we have to use a second system which will recombine the two beams, and that is the reason we are using two Wollaston prism. And this method is actually the currently no one uses the two standard Wollaston prism. So this after the invention of the modified Wollaston prism, people are using modified Wollaston prism. So this method is developed by a Polish scientist. So his name is Georges Nomarsky, and he from his name we are using the modified Nomarsky prism in our differential interference contrast microscopy, and later it has been means modified also. And one famous microscopist, you must have heard the name Carl Zeiss. So he also has exclusively used this differential interference contrast microscopy in his research. Okay, now coming to the DIC optics. So what are the different I have explained the mechanism, but how the optics work we will see first. So what are the different components? So though this component looks a little bit complicated, but there is nothing to worry about, because you only remember the setup. It's more or less similar to a light microscope. So only thing we have to worry about that there are four additional feature. One is a polarizer, another one is a condenser DIC prism and objective DIC prism, and then the fourth one is analyzer. So there are four key components to this differential interference contrast microscopy. We have to see what are those four key components, and what is the role in this interference contrast, then we will be able to understand. So here you see the first component is called polarizer. We know polarizer from our session previously. What does the polarizer do? The polarizer's job is to randomly, so here I have told that polarizer job is to do this. From randomly polarized beam, it should be able to give us a linearly polarized beam, right? So that is the job of a polarizer. So we have introduced polarizer in our DIC system. Then comes the new feature that we are going to introduce, that is called as condenser DIC prism. So this condenser DIC prism, or you can say this one is Wollaston prism. Here I am telling condenser because it is staying from the it is staying in the front side of the condenser. This is our condenser, this is the condenser lens. Actually this is the condenser lens. Okay, since I want two different kind of beam, so the job of this condenser DIC prism is to break my single ray into one ordinary ray and another one is extraordinary ray, right? So the role of condenser DIC prism is to do that. Now condenser DIC prism has done this. Wollaston 1 here, the condenser DIC prism has done its job. Now two beams will be going, as you can see, and these two beam ordinary ray and extraordinary ray, they will be mutually perpendicular to each other. Okay, so they both are going here you can see, and they are interacting with the specimen here, and from after interaction with the specimen, based on their constructive interference or destructive interference, they will go. They are also going. Now they have passed the objective as well. Here you can see the role of objective is not to do anything with the path length or something, the path length, because based on where they are coming from, the lens acts accordingly. But now after objective, after these two rays pass the objective, we can see that there are two different set of rays are there. One is O ray and E ray, same, but we for an image formation we need a single ray, right, which will contain all the information about a point or a feature in of our object. So what we will do, we will put another DIC prism that is known as the objective DIC prism. So here the condenser DIC prism is breaking the beam. So objective DIC prism, the role is recombining the two beam. Okay, so here the objective, you can see the objective DIC prism recombine the two ordinary ray as well as the extraordinary ray. And since and here in this case, so that means the role of this Wollaston 2 prism, that is important out of all these four components, to create interference and also to create image formation. Because if we do not keep this Wollaston prism for if we do not create, then we will get a blurry picture, or even if we get some picture, that will be giving us a double refraction kind of image. So that is why this objective DIC prism is one of the most important feature in DIC optics. And then finally we have combined the Wollaston 2 prism has done its job, and then finally we have the last component, that is called as analyzer. So the role of analyzer is to see which light is coming, like whether it's plane polarized light, whether it's elliptically polarized light, and according to its axis it will transmit the light. Okay, transmit the plane polarized light, so that they will interfere and then generate a contrast in the image. So the four component, so the analyzer, what does it do? According to its optical axis, it will transmit the polarized light, whether it's linear, whether it's circular, whether it's elliptical, any kind of polarized light, it will transmit through. So there are four components. One is polarizer, Wollaston 1, then here this is the third component, and this is the fourth component. So these are the four components which we have to see. We have to check that they are working properly or not in our DIC optics system. Okay, and so now we have talked so much about the DIC prism, that this prism is breaking one single ray into two different set of ray, and what is happening inside the DIC prism. What is the DIC prism? We'll look into it. So the DIC prism, as I have told, we have discussed, we have also gone through many times, that is called as Wollaston prism. Okay, so this name is also given, and it is a beam splitter. Okay, since it is splitting the beam in two different ray, that is O ray and that is E ray. And another thing, do not get confused by this E ray, and there is another thing in polarized light, that is E vector. So these things are not same. E ray means extraordinary ray, here E vector means electric vector. Okay, though they will come in many when you read any textbook or go through any articles, they might come same as E ray, E vector, but they are not essentially same. Here E ray means extraordinary ray, and here E vector means electric vector. So what does this Wollaston prism do? So it's a beam splitter which breaks breaks the ray into O ray and E ray. And how is it made? It is made using two wedge shaped quartz. Here if you can see this image, if you can see a there is a wedge. So this is a three-dimensional image. So there is a wedge which connects this line. Let's say this line is AB and this line is CD, which connects AB and CD. Okay, which connects AB and CD line, that is the their plane. So that is where the two wedges, that is so it's a if we are considering this is a triangle shape and also this is another triangle shape, so this is where these two have met. So this is a the Wollaston prism is a two wedge shaped quartz. And why specifically quartz is taken? Because quartz is birefringent. Okay, last lecture we have gone through this. The quartz is birefringent, that is why this quartz is taken. Or sometimes also we have in a specific application we can take calcite, because calcite also do double refraction. So that is why this quartz is taken. And here if you can see, so there are two different kind of, so let's say this is picture 1 and this is picture 2. And picture 1 is known as the, writing here, this is what known as a standard Wollaston prism, and picture 2 is known as modified one, and this modified one is known as the Nomarsky. So here if you can see at the down image here in the standard Wollaston prism, what happens, the one beam is going like this, and then where these wedge, both the wedge shape, where they meet, from there one is going in ordinary ray and another one is going in another direction, extraordinary ray, right? And their electric vector, ordinary ray and extraordinary rays electric vector, they vibrate mutually perpendicular to each other, right? And since one beam is getting converted to two different beams, the interference in this case, you can see the interference plane in a standard Nomarsky prism is cut in such a way that the interference plane lies inside this quartz. Okay, so here the crystals have cut in such a way that the interference plane lies inside the quartz. So that is the difference between a normal the standard Wollaston prism and the Nomarsky prism, the position of the interference plane. So what happens when position of the interference plane stays inside the quartz, and what happens when the position of the interference plane stays outside of the quartz, outside of this prism. So in this case, in the case of first prism, what happens, the interference plane generally when two beams are splitting, or even the two beams are combining at a place, then we want that interference plane to lie outside. Why we want to lie we want this thing to lie outside? So that if this interference plane lies outside, then accordingly we can put our objective lens as well as we can put our condenser lens. We need not to what we can do, we can fix our condenser lens position, and as well as we can fix our objective lens position. But if this interference plane lies inside the quartz, this prism, then we can't fix our condenser lens as well as the objective lens. Why? What will happen in that case? A little bit of displacement of this interference plane, let's say in our optic system, will create a distorted image, right? So that is the reason here the interference plane in a standard Wollaston prism, it is not preferred. It is not that it will not give image, it will give image, but it is not preferred that the interference plane lies inside the prism. Rather than that, if and why the interference plane is lying inside the prism, here if you can see, so in a standard Wollaston prism, what happens, this this optical axis, you can see this is the optical axis, let's say for this this side of quartz, and this is the optical axis which is lying a little bit left to right for this side of the quartz. So they are parallel to each other, right? They are parallel to the outer surface of the prism, right? So here, due to this case, when this case happens, then the standard Wollaston prism is created, and when the standard Wollaston prism is created, the interference plane lies inside the prism, which is not generally preferred, right? So that is why what Nomarsky did, instead of keeping both the optical axis of this wedge shaped quartz parallel to each other, what he did, he kept one optical axis parallel to the outside of the quartz and another optical axis he kept a little bit oblique in a little bit angular shape. Here you can see, right? So little bit angular. So one will be, so this optical axis is going to the plane of this screen, and that means this is also parallel. This is a parallel one, while this is the oblique one. So this is the difference between Nomarsky prism and Wollaston prism. In Wollaston prism, the optical axis of the edges, they lie parallel to the outside surface of the prism, while in Nomarsky prism, one surface will be parallel while another surface will be oblique, and due to that the interference plane, it lies outside. So since interference plane lies outside, so accordingly we can design prism in such a way that the plane of the interference plane, if it lies outside, then we don't have to worry about the refractive index of this thing again, because the interference plane, let's say I want to put I want to create this interference plane in a back focal plane, so that I will see some diffraction, what kind of diffractions are taking place from my optical from my image. Then I can play around, then I have freedom to play around with my image in that case. But if my interference plane lies within the Wollaston prism, then I don't have much freedom to decrease or increase any of the feature, because the interference plane, if I'm going out of this range, then the interference plane will be going out and the interference will not basically take place. So this is the idea behind the standard Wollaston prism as well as and the Nomarsky prism. Okay. So now if we are talking about the DIC image, how the image is formed. So the image. So how the image is formed, and we have seen the DIC optics. Now we will see how the images are formed in a system. So the image is generally formed by two types. One is ray tracing, another one is wave optics. So we have to consider both of them. So the picture here I have shown is of ray tracing. How the image is formed, we have to see. In ray tracing means what? We have to observe the action of DIC microscope as an interference device, like I have mentioned here. So what do we do? How the interference happens? So simply we have to see. So here, let's say I'm taking three cases, one each. Okay, A, B, C, three cases I'm taking. In the case of A, let's say, what will happen? No, so this is the specimen stage. This is the specimen stage. This is the specimen. Okay, this violet color is the specimen. So here if you see A, B, C, three conditions I have taken. Ray tracing means there should be, like we saw previously, there should be a little bit path difference between O ray and E ray. But here, for them to have a little bit path difference, in the case of A, when I am taking, there are only this O ray and E ray. There are two different set of ray are there. We can see that the O ray and E ray, they are going through only the stage of the specimen. No, they are not interacting with the specimen itself. So in this case, what will happen? The O ray and E ray, what will happen? They will not have that phase difference, or they will not have that optical path difference. So if they will not have optical path difference, if their optical path length will be same, then it will be a constant derivative of any constant will be 0, right? And similarly, let's say they have gone through here, they are a linearly polarized, so here they have gone like linearly polarized wave, and from linearly polarized wave they have gone and they have been splitted in O ray and E ray. Here means they are the O ray and E ray. Before that they have been splitted, and here this is the combination happened, right? That is the Wollaston prism 2. The combination happened, and after the combination, same thing they have gone. So there also they were linearly polarized. Here also they will be linearly polarized, And if they are linearly polarized, generally in polarization microscopy, what we do, polarizer and analyzer will not be in the same direction. So the analyzer will always be rotated in some angle as compared to the polarizer, right? And since they are coming in a particular direction, in a they are linearly polarized in the same direction as they are coming from here, the analyzer, what it will do, it will block them, it will not let them pass. Why? Because the polarizer and the analyzer, what will they do, which generally they are kept at 90 degree to be exact. So they will so since this is the analyzer, okay, so and that will block the this linearly polarized transmitted wave, right? So we will not be able to see any contrast. Let's say two waves are coming in the case of B. In the case of B, same linearly polarized waves are coming, but they both are interacting with the specimen. Since they both are interacting with the specimen, they will have whatever path length they will have, same thing also will be here, that the optical path length will be same, right? Okay, so in that case they might be different, the optical path length might be different, but that difference is not significant, so that we will be able to see the changes in the derivative. So that is why I am saying they are also in this case also same. But after here also, what will happen, the same polarization, let's say this is linearly polarized light, is going and splitting in two rays, and after combination, same thing, the linearly polarized light will remain as it is. So this wave will also be blocked, right? Now coming to the case of C, where one whether it's ordinary ray or extraordinary ray, one of the rays will go through the specimen, another ray will go through the specimen stage. Then what will happen in this case, the linearly polarized light, let's say if we are sending, then after interacting, it will become the elliptically polarized light. Why it will become the elliptically polarized light? If you remember, in the last class I have told that the E vector, let's say, this is the E vector, and so it's the electromagnetic radiation I am drawing. So you just have to imagine this thing. Let's say this is the perpendicular one will be the E vector, which is in XY plane, and another one will be the magnetic vector, which will be in XZ plane. In this figure I am talking about, then they will not interfere, rather they will give the addition. And this is so this is E vector, let's say this is E1, let's take, and another one is E2, two electric vector of two different waves. So since they are mutually perpendicular to each other, two different beams having electric vector called as E1 and E2, and then since they are perpendicular to each other, they cannot merge directly. So what will they give? If one is coming in this direction, another one is coming in this direction, so the resultant will be the vector sum of these two. And that is why instead of linearly polarized light, we will get an elliptically polarized light. Okay, so the diagram unfortunately I don't have in the last tutorial. You can go and refer to the elliptically polarized light. So it will be something similar to so it's like this, but these are all ellipse. Okay, so this will be the diagram of an elliptically polarized light. So that means if there is an optical path difference, so the linearly polarized light here will be the elliptically polarized light. And since the elliptically polarized light is having electric vector in an angle, in an angle which might have also an axis when the polarizer according to the polarizer here situated. That means what I am saying is that, let's say I am having my resultant electric vector in such a way that it looks like this, and my analyzer, I have placed my analyzer in such a way that it will give, my analyzer is placed in this way. Let's say the simplest case I am taking, my polarizer was giving initially linearly polarized light like this. Since my analyzer is situated like this, so it was completely blocking in case of A, in case of B. But now I have got a resultant wave whose E vector is like this. Okay, so now what will happen if I have an analyzer whose axis is like this, then out of all these ray, out of all these E vector, one E vector will pass through, right? And that one E vector will pass through, and using this one, that means I am getting some optical path length difference, and that difference will be converted to the derivative. Whatever I will get, so I will get the derivative of this optical path length, because I used linearly polarized light and I have got elliptically polarized light using this prism combination, no mask prism. So this thing I will get, and that is how I will be able to form the DIC image. So this is by ray tracing DIC image. But what I will do in ray tracing, even in ray tracing here in this case, the difference might not be that high. So in that case, what I will do, I will consider I will consider not only ray tracing, but I will consider also the wave optics part. So what does wave optics part means? Wave optics means there are two different wave fronts. Since I am talking about beam, ordinary ray and extraordinary ray, there will be two different wave fronts, right? So these wave fronts, if I take any point in the wave front, so they represent, what do they represent? They represent the localized region of phase retardation. That means if I am taking a wave front between O ray and E ray, so any point or any section, I am choosing any section between those rays, so there will be definitely a phase lag between them. I am talking about this case, the C case, right? So what I will do intentionally, so here first I am going to show you what will happen in C case. So now we will not talk about A and B case, right? We are only talking about C case. So what I will do in that case, so since there is not much difference between the O ray and E ray, because the O ray and E ray, the phase lag is there, but the phase lag is not that much high. So in that case, what I will do, what I get this kind of image where you can see there is the dark central interference in here. You can see this point. If I am talking about this thing, there will be a dark central interference. That means that is the zeroth order interference fringe. Zeroth order means that there the negative, destructive interference is taking place, right? So here if you can see, generally in case of C, which I showed in the previous slide, so in case of C I will get a picture or an image like this. But here what I want to say, what I want to imply is that though I am getting a picture like this, but I am getting some dark fringes in the middle, and also this dark background I am getting. So I want to still view my image in a better way. So how will I be able to do this? So in that case, what I do, I intentionally I introduce some bias retardation, or that is called as the phase retardation in my both of the two waves, right? And this phase retardation, let's say I put some kind of retardation between my objective ray and my my O ray and my E ray, that is ordinary ray and extraordinary ray. Then what will happen? This, if I retard my any one of the ray, then the optical path length, the gradient in the optical path length will also increase. And if my gradient in the optical path length will increase, similarly my amplitude difference will also increase, and same my intensity difference will also increase. And due to that, what I will get? I will get an image like this. That image, you can see the dark in this. If you are looking at this figure, this is a dark shadow plus bright, some this side some bright highlights are there, right? And so this dark shadow and bright highlights I will get when I intentionally introduce some kind of retardation. That means some kind of phase lag. Here you can see the phase shift is mentioned in the x-axis. The phase shift is not that much high. Now intentionally in the down figure I introduce some phase shift. We have discussed how we can introduce a phase shift in amplitude object and phase objects we have earlier seen. So now intentionally I have introduced some sort of phase shift which will give me a gray color background, but the image of the particles, let's say these are the particles I wanted to see, the image of the particles I'll get it dark shadows plus bright highlights. Since I'm getting a bright highlights and dark shadow, so it is looking like a three-dimensional image, right? It is looking like these particles are floating in space. Let's say if I'm considering this as a vacant space, so these particles are these particles they are floating in vacant space. So that is why I have told in the first slide that this DIC microscopy will give you a relief like or a shadow like appearance. So these are very minute particles. It might give you appearance like it has some topological difference. Topological difference means this side means it is not a perfectly flat surface, rather it has peaks and valleys. So this kind of appearance it will give. So but it might be due to that, but in DIC microscopy we should not interfere, we should not interpret that this kind of bright highlights and dark shadow will give necessarily the necessarily depict the three-dimensional features. Okay, so that we have to be careful about. And here we can see the phase shift and shear axis, and if we are plotting the phase shift and the shear axis, then here two things we have to remember. One will be wavefront. So these are the wavefronts. So wavefront width will give you magnified object diameter, and the depth here, this will give you the amount of phase retardation. So here the amount of phase bias we have given like very low. Now we have retard the phase, so that is why it is this kind of image we are getting. At least better than this image. We cannot say that it is giving the correct feature because it is decepting us, but still we are getting a better contrast image. And this condition is known as where we are getting a dark background and a central dark fringe. This is known as the, I'm writing it here, this is known as the extinction condition in DIC microscopy. Okay, so these things we have to remember. And yeah, so that is all about the differential interference contrast microscopy. Now we will come to the last segment of our microscopy, that is known as the fluorescence microscopy. The fluorescence microscopy means so we will see for how the fluorescence microscopy works. So before that I just want you to look at this picture here. This picture you can see some bright lights. Some bright lights are coming from this section. If you are looking, then some blue lights are coming from here. This is green light, then this is red light. So some bright color we can see. So this colorful image we can get through fluorescence microscopy. And generally fluorescence microscopy are not introduced in if we want to see any normal optics, like if we want to see the fluorescence microscopy in simple terms, it is used for a specific purpose. We cannot use the fluorescence microscopy for all of our samples, the general samples. It has a specific purpose, and the sample should be we will see the sample should be able to radiate the fluorescent rays. In fact, when electron interacts with the matter, fluorescent rays are coming, but the amount of fluorescence that the matter gives depends on that. We put our material, we put our object under the microscope to see fluorescence microscopy. So it is basically the improvement of microscopy to see biological cells and protein, different structure in the protein. Mostly we see those kind of images in using the fluorescence microscopy. It's also used in thin film technology and optoelectronics. So there are two factors which are used in fluorescence microscopy. One will be two system which are crucial for this fluorescence microscopy. One will be interference filter, another one will be dichromatic mirror. We'll see what that interference filter and dichromatic mirrors are. And also for fluorescent microscopy, like I said, it should not be like random. We should be choosing a random material and we want to see it through fluorescence microscopy. No, so we have to choose a proper fluorophore. What does the fluorophore mean? We'll see. And we have to choose a proper filter. Why we have to choose a proper filter? So that it emits the particulars or a specific wavelength, and we have to choose an illuminator, an illumination system which will give us the fluorescence microscopy. We cannot choose a random illumination system which will give us fluorescence microscopy. And like I said, these are generally used, this fluorescence microscopy, to view the cellular distribution or the study of protein and the extent of enzyme reaction. So like this, cell viability and cell function, like this biological sample, we want to see using this fluorescence microscopy. So what does the fluorescence microscopy comes from it? There is a term called fluorescence. So what does fluorescence mean? Fluorescence means emission of photon by atoms or molecules whose electrons are transiently stimulated to a higher excitation state by radiant energy from an outside source. So this is the textbook definition of a fluorescence. So but if we want to visualize what fluorescence radiation means, that means simple. Let's say my object is here, okay, and I am impinging some incident light, and this incident light is carrying some amount of energy, and this energy somehow is transferred to this some of the atoms in this object, right? And here, after getting some of the energy from this incident beam, what will happen? Then some of the atoms will go. Why they will go? Because basically the electrons, not the atoms, will go. Basically the electrons will leave their ground state, and when the electrons leave their ground state, they go to different kinds of excited state. Okay, so electrons in the atoms, they will, so let's say this is the ground state and these all are excited state. So they will leave their ground state and go to the excited state. But the problem is they got excited and went, but they cannot stay there for far too long, because ground state is the state where the energy is minimum, okay, and they cannot stay in the excited state because their energy is more than the minimum value. And every system in our universe wants to minimize its energy, so that is why they have to come back here. They have to come back to the ground state, and that is the reason while coming back they should release some amount of energy, right? And this amount of energy are if they release it in form of radiation, then these are the fluorescent radiation. Okay, so this is the emission of this energy is what called as fluorescent radiation. And here if you see the fluorescence, how the fluorescent radiation happens, if you see, there is this is a diagram I have given. This diagram is called a Jablonski diagram. Okay, here you can see this is the ground state. These all are the energy level, and this is and inside the energy level there are different sub levels are there, which is not concern to us. So what do this ground state and excited state, what are their roles here? So since let's say energy is coming in the incident beam, energy is coming here, and it gives energy to a few electrons which are present here, right? And these electrons now have sufficient energy to cross this barrier to go out of this ground state, and they went to some S1 and S2 excited state here, but they cannot stay there for far too long. So what will they do? They instantly come back, and due to this, while they come back, they radiate some amount of energy, and that energy we get if we are able to catch those rays, those radiation, they give up that higher amount of energy in terms of radiation. And if we are able to put a detector which is going to detect that radiation, then that microscopy, that technique is called as fluorescence microscopy. Okay, and so that thing is called as fluorescence microscopy. And there So this is the ground state, but the excited state, there are two different kinds of excited state. For now, we will see what those excited states are. One is excited singlet state and another one is excited triplet state. And these state, just to know the what are these states. So these states are named like these states are identified and defined based on the electronic spin number. So spin rotation, how the electron spin quantum number, based on them, based on those numbers. So these values are given excited singlet state and excited triplet state. Okay, so we will know that this much, that the based on their different spin state in the excited electron of the excited electron, so these states are given. Generally what happens, when an electron gets energy, it goes to excited singlet state, that means this state, right? And directly when it comes back, so it comes back and gives the fluorescence radiation. If we are able to catch that fluorescence radiation, then it is good for us, we will use it in our microscope. But it is not necessary that always when it comes from excited singlet state direct to ground state, it will give us fluorescence radiation. Why? Because sometimes internal conversion also happens. What does that internal conversion mean? Sometimes this extra energy may go from the system in the form of heat. If it is going from the system in the form of heat, then we cannot catch it, right? Because we want some sort of radiation. If the heat is coming, then we cannot catch it. Our detector cannot catch the heat. Then the process is not. So this is not called as sorry. This is not called as fluorescence radiation. This is what called as fluorescence radiation, because the radiation should we should be able to get that radiation not in the form of heat. And then this is one system. So what happens if from excited singlet state, once the electrons are excited from here, let's say from the ground state, they goes to excited singlet state. But from excited singlet states, there is another transition state. So this excited triplet state is known as another transition state, and that they from here to here when they go, that process is known as intersystem crossing. From excited singlet state, they went to excited triplet state. So that is known as intersystem crossing. So when they go there, in that case what will happen, from that method also, excited triplet state, they can come back again giving some amount of energy, and that is also known as fluorescence radiation. But there is like the electrons giving some energy, giving up energy in the form of heat. Here also there is provision of heat. Instead of giving fluorescence radiation, the extra energy may go out of the system giving heat. Okay, so this is also a possibility here. But then what is the difference between coming of an electron from excited triplet state to excited to ground state, and from excited singlet state to ground state? There is a difference of time, right? So when this electron comes from excited singlet state to ground state, that process is called as fluorescence. But and that process, I'll put it here, yes. So here fluorescence happens almost simultaneously. That means 10 to the power minus 9 to 10 to the power minus 12 second. The time lag is there. That means the one electron is getting energy and immediately it is going to excited state and again it is coming back. That means this process is almost simultaneously happening. Okay, and this is what called as fluorescence. But when the electron comes from excited triplet state to ground state, there the time lag is there. That means it is not happening simultaneously. There is a time lag of 10 to the power minus 2 to 10 to the power 2. And this process is known as phosphorescence. Not fluorescence, but that is phosphorescence. Okay, so this is what the triplet state. And this is what the singlet state. Excited I am talking about. Excited singlet and excited triplet state, right? And do not get confused this phosphorescence. There is another term called bioluminescence, where there also electrons are excited, but it is a chemically driven process. It is not that we are not giving extra incident beam to we are not giving energy to the sample, but the object is itself, inside the object some chemical reaction is going on, which in the process where the electrons are excited, and that is how we are getting luminescence. Okay, and this excited triplet state, right, we have to be aware of that. In this excited triplet state, there are two phenomena which can take place. One will be photo bleaching, and another one will be production of free radical. That means production of some unpaired electrons, right? Production of free radicals means the production of unpaired electron, and there is another process called photo bleaching. We'll see what photo bleaching means. So we want to avoid this photo bleaching. Why? Because this photo bleaching will, if the photo bleaching happens, then it will reduce our fluorescence efficiency. Okay, fluorescence efficiency of the object. So to get to know some of the basic terms in fluorescence microscopy, one term is fluorochrome. So fluorochrome means the molecules that are capable of fluorescing. Fluorescing means anything which will from which we are going to get light. Okay, and these fluorescent molecules, and these fluorochromes are known as also fluorescent molecules, fluorescent dyes. They are called like that, right? And there is another term called fluorophore. These fluorochromes actually, they are attached to a macromolecule, right? These are the molecules. Here fluorochromes are the molecules, but these fluorochromes, they are always attached, or they are always tagged with a macromolecule, which is known as the fluorophore. And this fluorophore is a chemical moiety. Moiety means part. Okay, so it is a chemical part of a large macromolecule which is able to produce this fluorescence. So there are different these are the different terminology which you have to actually keep in mind in case these terminologies come in the exam or anywhere. And this fluorophore are actually they are dependent on atomic structure of a material and electron resonance property. Okay, and what are there inside the fluorophore? Several unconjugated double bonds which generally contains the nitrogen atom, the sulfur atom, as well as the oxygen atom. Okay, and here if you see this is a absorption spectrum, this image I have given. So here if you see how the fluorescence occurs, here absorption spectrum we can see, right? And here the emission spectrum. See the absorption spectrum, you can see that there is a difference between the peak of the absorption spectrum as well as the difference between the peak of an emission spectrum. Okay, so these are the two different phases, two different spectrum that we have to see in fluorescence microscopy, and this difference is known as the Stokes shift. Okay, this is this is a very popular terminology, the Stokes shift. So the difference between the peak of the absorption wavelength and the peak of the emission wavelength, this is known as the Stokes shift. And since why there are two spectrum involved, because as we see here, one will be coming with the incident ray, that means, and this ray has to be absorbed by this material. Okay, and then only it will gain some energy, and then finally from here in going to the higher excited state, it will emit something. So that is why excitation spectrum, which will excite the material, and then emission spectrum, which will where the higher the electrons in the higher energy state will emit the spectrum. Even if so we can say that in fluorescence microscopy we will be using let's say we want to use a monochromatic source. In that case here in the image, if you can see, then I have used from 400, I have used my absorption spectra is from 400 to 550. You can say that why I will take from 400 to 550. I can only take a particular wavelength, let's say 450. Even if you use a monochromatic source like laser or LED, anything, still you will be able to, the emission spectra, you can get a single source for this one, but for emission spectra you will not be able to get a single wavelength. Why? Because there will be always a broad spectrum of longer wavelength. The reason for this broad spectrum of longer wavelength, because the electron will release some amount of energy. They might consume all the energy that is coming from absorption spectra, right? Or the excitation spectra. but they will, in the state of higher state, they will release some amount of energy, whether it's in the form of heat, whether it's in the form of vibrational energy, they will always release some form of energy. And then even they even they got the one energy to go, they got one energy to go to the higher spectra, they will be losing energy in a broad range, right? So that will give us a broad range of emission spectra, right? And so this is the basis for which we have designed the fluorescence microscopy. And yeah, this is one of the properties. It's properties of that light fluorescence related to the fluorescence microscopy, that is Stokes shift, the difference between wavelength or energy, because wavelength is associated with energy. So the difference in wavelength or energy between excited and emission fluorescent. So in practical, the difference between excitation and emission maxima means the peak here, the peak here, this is the maxima. Okay. And so there is another term I want you to know, that is called as molar extinction coefficient. That means the potential of a fluorochrome. The fluorochrome is, if you remember, the molecules that are capable of fluorescing. That is the potential, how much it is able to emit the radiation, right, after absorbing the photoquanta. Okay, so that is known as molar extinction coefficient. And there is another term which is important, that is known as quantum efficiency, QE. Okay, this quantum efficiency is defined as the fraction of absorbed photon quanta that is re-emitted by the fluorochrome. That means how much it is, let's say this is my object, how much it is absorbing, and then let's say the electrons are going to a higher state, and how much it is coming, how much the electrons are radiating. Okay, this is known as quantum efficiency. So if we are talking sorry, if we are talking in form of quantum efficiency, then it varies for different fluorochromes. The quantum efficiency value varies. If under also it depends on the condition, like if we are using a fluorescent dye which is alkaline, that means the pH, if it is somewhat close to the alkaline medium, if you are using, the quantum efficiency comes to 0.9. And if we are using a neutral pH, so this is the alkaline pH, so if we are using a fluorescent dye which is having the neutral pH, then the value lies from 0.3 to 0.6. So this quantum efficiency, these are the value of quantum efficiency. And similarly the Stokes shift also, the value of Stokes shift, so this lies, it's from a few to several hundreds of nanometer, it is there. So generally the value is 25 nanometer also. For 25 to 200 generally the value stays like this, the value of Stokes shift. Okay, so these are some of the terms that you have to see, because they are associated with the fluorescence microscopy. And so what are the hindrance then to fluorescence microscopy? There are two hindrance, one is quenching, another one is photo bleaching. What do? They reduce the amount of fluorescence. If we are not getting enough fluorescent radiation, then how will we use that light, that radiation to impinge on our material and then finally get an image? So these quenching and photo bleaching, what do? They reduce the amount of fluorescence. And quenching means the reduce of the quantum yield. Okay, that means it somehow from the more quantum yield we get, the more value, the more contrast and the good image we will get. So the quantum efficiency value, photo quenching, what does it do? It reduces. And photo bleaching means the permanent loss. Photo bleaching is one of the most disadvantage that can happen to our fluorescent material, the permanent loss of fluorescence by a dye due to photon induced. So it is a chemical damage that is happening to our material. So why I am saying this chemical damage? Because remember, fluorescent microscopy is generally used to view biological samples, cells, proteins, all these things. So they are our day-to-day, let's say metal, if I am talking about a metal, hard ceramics, then they might not be susceptible to the chemical damage, but the a biological cell, it is susceptible to chemical damage, because electrons with high energy, if they are continuously impinging on your material, then chemical damage happens. Why? Because there will be modification in the bonds as well. So that is why the permanent loss of fluorescence happens. Okay, and the optics is like this. So these things I have mentioned it here. So there are three things we have to see in a fluorescent microscopy. One should be this one, that is our light source should be bright, so that we will get proper fluorescent radiation, right? And this light source is generally used, so there are different set of light. One is, I think, one is used there, metal halides, and xenon lamps sometimes are used. Another thing, xenon lamps, metal halides, and one more source also, it is also used for fluorescent microscopy. So it is used in epi illumination mode. So epi illumination mode, remember, we have come across this term. So epi illumination is in reflectance mode, and there is another illumination mode is also present, that is trans illumination mode, which is transmittance mode. AP means so reflectance. So what happens here, if you just look at this diagram, you will be able to understand the entire fluorescent microscopy. So we are impinging some sort of light here. So since this light is coming, so it is having a specific energy. So there is an exciter filter is there. Okay. So I'll first tell the component. So this is a bright, this is the light source. This is an exciter filter. Then this blue color, if you see this shape, like there is an object is that is known as the dichromatic mirror. Okay, so that is another component. Then this is objective lens and specimen would be there, and then there is another thing called barrier or emission filter. So there are three things which are important for us. One is this exciter filter, another one is dichromatic mirror, another one is barrier or emission filter. What happens when this exciter filter comes in between the light source and this dichromatic mirror? What it does, it allows a specific wavelength of light to pass through it. It does not allow every wavelength of light to pass through it. Let's say this is, we are impinging white light, right? Or in this case I'm saying white light, but even we can impinging a monochromatic light. So it allows a specific, this exciter filter allows a specific wavelength of light. That means wavelength is associated with energy. It allows a specific wavelength of light to impinge on the dichromatic mirror. What does this dichromatic mirror do? This dichromatic mirror, if you can follow this green ray, this dichromatic mirror reflects this beam, and what does it do? The beam falls on the specimen here. Okay, this is the specimen. This red one is the specimen here I'm talking about. And once this this green light comes and falls on the specimen, since the specimen is a fluorescent dye, some of the electrons will be excited and go to higher state, then the fluorescent radiation comes. Since the fluorescent radiation comes, what it will go? It will again go in the same thing, right? In the same direction it will go, but not necessarily in the same path. It will go in the same direction. Now the dichromatic mirror has been designed in such a way that it will allow the transmittance. Initially it was reflecting the green light, but now it will allow the red light here to pass through it. And once it will allow the red light to pass through it, there will be another thing called barrier or emission filter, which will also allow that specific wavelength to pass through it, and from here we will be able to see the image. So this is the optics behind the fluorescence microscopy. So there are three things important. One is excitation filter, dichromatic mirror, and barrier or emission filter. So this is the concept behind the optical microscopy. So here I have written down all the their functionality, the excitation filter, dichromatic mirror, and barrier filter, right? So the role of the barrier filter is to transmit the band of fluorescence wavelength while blocking any residual short excitation wavelength. It might happen that just here, it might happen that not necessarily only the fluorescent wavelength will go, but also some of the higher energy, that means the lower wavelength will also go and pass through pass through this one. Like some of the green waves also it will go. So it will pass through this thing, this dichromatic mirror. That process is, I will tell, that process is known as bleed through. Okay, so that bleed through, if that thing happens, then that the role of the dichrome, the barrier or emission filter, is to completely block that thing. Okay, and the fluorescent wavelength then forms the image on the eye or camera. Okay, and there are different kinds of lamps are there. Yeah, another one is mercury lamp. Yeah, metal halide, mercury, or xenon arc illuminator. And sometimes if we want completely monochromatic, we'll get laser or LED, that means light emitting diode. So proper wavelength, we should use an illuminating source that is giving us proper wavelength and sufficient intensity. And epi illuminator lamps are used generally, and lamp plus collector system, connector, tube, relay length, these are the different components of our fluorescence microscopy, that optical system. Okay, filters are used, colored glass filter and thin film interference filter. So these are different kinds of filters that are used. And yeah, one of the major components that we have seen is the dichromatic mirror. So dichromatic mirror here is used as a beam splitter. Why it is used as a beam splitter? Because it does both. It reflects a certain type of beam, and it allows the transmission of a different kinds of beam. That means it is discriminate. Even if we are allowing, let's say we are impinging a 5, 6, 7 different types of beam, it is discriminating between all those beams. It is allowing one type of beam to go and reflect the specimen, and then when another type of beam is coming, it is allowing transmission through it. It is not allowing transmission for the same kind of beam which it was reflecting earlier. That means it is not allowing the green color beam. If you remember from the previous slides, it is not allowing the green color beam to go transmit through it. Rather, it is allowing the red color light to transmit through it. So it is a precise discriminator. The dichromatic mirror is a precise discriminator, and it stays 45 degree with respect to the optical axis, like this. This is the source, this is going, and then this is the specimen, and then this is allowing like this. So it is clearly discriminating between the rays, okay, reflection and transmission. And it is designed in such a way that only at certain boundary wavelength, at certain it is allowing a certain wavelength to reflect, and it is allowing a certain wavelength to transmit. So this is the role of a dichromatic mirror. Okay, and if we see, so here if you can see in this image, if you can see the excitation window is this one and the emission window is this one. So if I can put from my observance versus wavelength spectra, I think this image is a little bit small one, but if you look carefully here to this image, the down image, if you see, then all this kind of thing, that means my shorter wavelength, this wavelength is used as my incident ray to excite the electrons of my material. So I need not to transmit it. This is a transmission in y-axis. You can see this is the transmission versus wavelength in x-axis. So I need not to transmit this wavelength through my reflectance or my dichromatic mirror. What do I need to do? I need to transmit this one, right? Since I need to transmit this one, you can see I can choose my dichromatic mirror in such a way that what will happen, I can coat my dichromatic mirror with such dielectric materials is that they will only allow a wavelength beyond this one, higher wavelength beyond this one, so that I will get transmittance of the longer wavelength. Remember, the higher energy is coming and lower and higher energy is coming and hitting the sample. Then after getting the electrons going to the higher excited state, they are losing some energy. That means the wavelengths, shorter wavelengths are coming to the sample, and then when the fluorescence happens, the longer wavelengths are happening. So this is shorter wavelength and this is longer wavelength happening in the emission window. So generally the shorter wavelength are come from the this window. The initial window is excitation window. So this is the excitation. You might have, okay, I'll write it here. So this is the excitation window. The shorter wavelengths are coming, and then when they lose energy, the longer wavelength are generated. So this is the emission window. So that is how I will design my dichromatic mirror. And the transmission profile, if you can see here, it is this image. If you can see the high transmittance and low reflectance, that means this is a transmission versus wavelength curve I have put. So the high the peaks correspond to the high transmittance and low reflectance. Okay, and the trough, like here, this kind of feature, if I am coating my dichromatic mirror with such dielectric materials, is that the wavelength, it will only allow this kind of wavelength, then I will not be able to see anything, right? You can see, so this is the excitation filter which is allowing this kind of the lower wavelength, then the dichromatic mirror is reflecting this greenish color wavelength, and then emission filter is completely blocking them and transmitting through. And this green, for the green color thing, you can see the transmission thing is quite high for the emission filter. Okay, that is the role of dichromatic mirror. And there is another term called bleed through, that is transmission of unwanted wavelength. It is not necessary that the dichromatic mirror will always block the beam comes and it will always direct towards this thing. There is a chance that it will also allow some amount of transmission. So this transmission are called as unwanted, the transmission of the unwanted wavelength, it is known as the bleed through. And generally we design our dichromatic mirror in such a way that the bleed through will happen till 10%. Okay, I think yeah, what is the time? Yeah, so okay, so that will be the end of the concept for our optical microscopy. So here are a few problems. We will go through them quickly because they are conceptual, and I have discussed the same concept in the previous tutorial, but still we'll go through them. Okay, so yeah, till now, if anyone has any doubt, they can ask, or we will go through the question one by one. Some questions are conceptual and some questions are numerical based. So yeah, we'll go, there are few questions, we'll go through them. Till here, is anyone having doubts or any queries? Okay, if no one is having doubt, then we'll see the question number 1. So the question number 1 is, how should the initial focusing of the microscope be done? Yeah, what I have not gone through here is the method of method of preparation of the samples. That means we have seen in the videos that how the sample for an optical microscopy is prepared. That means cutting, then mounting, then grinding, then polishing, and then etching. So all those processes we have to go through that, and then there are different kinds of etching also which are done using chemical etching, and also thermal etching is also done. So those are the things also you should remember before you go to microscope to see a good image of your object. So related to, then if you put your object under the microscope, then how should the initial focusing of the microscope be done? Can anyone answer? Okay, A. So okay, so one has answered A, while the coarse focus moving the lens towards the specimen. Okay, that's the answer B. Okay, you can unmute yourself, otherwise yeah, that's fine anyway. So one answer is A, another one is B. Okay, so we'll see the coarse focusing, the initial focusing of the microscope. How can it be done? It is generally so the initial focusing we do by moving the microscope. Initial we will do the coarse focus, and then then we will do the fine focus. So there, if you see, there are two knobs will be there associated the side of the microscope. I'm doing these two knobs. So first we have to rotate this one will give us the coarse focus, and then this one will give us the fine focus. Okay, and so the initial with the coarse focus moving towards the moving the lens towards the specimen, and with the fine focus moving the lens towards the specimen, the coarse focus moving the lens away from the specimen with the fine focus. Okay, so the initial focusing is done by using, remember, this option, using C, moving the lens away from the specimen. First we do the coarse focusing, then we do the fine focusing, moving the lens up and down. Then we see how our features are looking like. So it's neither A and B, it is, the answer is C, with the coarse focus moving the lens away from the specimen. While we do the coarse focus away from the specimen, it is also, if you can think it in this term also, because since we are doing the coarse focus, this is, let's say this is my microscope, right? And if I am moving it coarse focus means I am doing focusing in vertical Z direction. Let's say if I am trying to get the focusing, and this is my sample, right? This is my sample, and I'm coarse focus means my upward and downward movement will be very high. Let's say if I don't get my focus correctly, and I try to keep on moving my lens towards the specimen, then what will happen? There is a chance that my lens will also hit the specimen. So in that case, my specimen will also be damaged. So in that sense, you can also remember that with the coarse focus moving the lens away from the specimen, the initial focusing is done. Okay, and this.
Excuse me?
Yeah.
Please go to the question 1.
Yes.
This is applicable when you have the vertical microscope. This is not applicable when you have the inverted microscope.
Uh, which one? Can you
See, question 1, two types of microscope, correct? One vertical and another is the inverted microscope, correct?
Yes.
We talk about the vertical microscope, when stage move, there is a chances of hitting. But if you talk about the inverted microscope, there is no chances of hitting.
Inverted microscope, that means
So this question, I think, maybe remodify.
so inverted microscope,
If you do that, how it will? There is no question of taking away, because already if you take, for example, 50x,
yes,
you will only doing the towards up, because your stage is moved. There is a safety feature is there. It will not hit at all. It will not go outside also.
the inverted one.
Yes, this is inverted one. If you talk about inverted, then C is not applicable.
Okay, so you are saying this question is for the normal microscope,
See, not normal. You have
like
to
the reflectant one.
vertical microscope.
Vertical
Reflectance
microscope.
is different.
Yes,
Vertical microscope only this is applicable.
Okay, yeah. I'll check with the inverted one. Okay, here you can write vertical microscope. I'm not sure about the inverted microscope, but I'll check and come back to you. Sure.
Inverted microscope, generally there is no chances of hitting.
Yeah. I'm getting the geometry. I'm getting, but I'll check and get back to you. Sure. And
Thank you.
So here the question 2, the specimen preparation is important in metallurgy because, so there are 4 options. A poorly prepared specimen can damage the microscope. Okay, a poorly prepared specimen will distract from features on the specimen. Only a well prepared specimen will reflect light. A poorly prepared specimen will corrode and resulting images will be misleading. So can anyone answer which one will be the correct answer?
B is the answer, sir.
Yeah, B is the correct answer, because a poorly prepared specimen can damage the microscope. That is not true, because the microscope the specimen can damage the microscope. This is not true. A poorly prepared specimen will distract from features on the specimen. Yes, if we are not preparing our sample properly, then it will distract from features. We will not get proper image. We will rather get distorted image. So this is correct. Only a well prepared specimen will reflect light. No, not necessarily, because a badly prepared specimen also reflects light. It might not give us bright light. The destructive light also, it might destructive interference might also take place. A poorly prepared specimen will corrode and resulting images will be misleading. Not necessarily the corrosion might happen. So the correct answer is B. A poorly prepared specimen will distract from features and on the specimen, and we will get misleading image, right? So B is the correct answer for this. Yeah, so this is another question. The red tint plate, also known as a full wave sensitive tint plate, increases the contrast in a polarized light microscope because it is related to polarized light microscopy, in the last lecture that we have gone through. So our eyes are more sensitive. So the options are, our eyes are more sensitive to red light, so it is easier to see the light and dark areas when there is a red tint plate. That is option A. That is, and then option B is the red tint plate only lets a small window of wavelengths through, so it increases birefringence. That is option B. The option C is the red tint plate displays the ordinary and extraordinary beams by an extra wavelength, so that small difference in birefringence cause large difference in color. And the red tint plate, the last option is the red tint plate increases the difference in birefringence in the material, so that different grain direction cause a greater difference in the color than just in polarized light. So anyone can answer what is the correct answer? Can guess? Okay.
Sir, I think D is.
The red tint plate increases the difference in with different grain directions. Okay. No, in polarized light microscopy. So we'll go through. Okay, we'll go through one by one. Our eyes are more sensitive to red light, so it is easier to know. That is not true, because we are able to see the visible spectrum completely. So more sensitive, the quantitatively we cannot define the more sensitive term. The red tint plate only lets a small window of wavelengths through, and so increases the birefringence. No, this is also not correct. Then the red tint plate displays the ordinary and extraordinary light beams, and so that small difference in birefringence cause the large difference in color. Yes, this is correct. The red tint plate increases the difference in birefringence the material, so that the different grain direction. Here the difference between C and D is that here the ordinary and extraordinary ray, when they are when there is a retardation, so what happens, the phase lag will be more, and then the contrast will be more. Here the red tint plate, here this is the thing, that the different grain direction cause a greater difference in color. Okay, so in this case we cannot say that different grain direction cause a greater difference in color, because the function of red, it is not a function of red tint plate. Okay, so the correct option would be C. Okay, yeah. So the next question is, contrast in reflected microscopy tends to be caused by, we'll see this one, variation in topography and differences in reflective of area. Option A, only difference in reflectivity of area. Option B, only topography. Option C, and variation in thickness of the specimen. So contrast in reflected microscopy, that means reflected microscopy is like this. And this is the object and incident beam is coming. So yeah, so the contrast in reflected microscopy tend to be caused by
A.
Which one?
A.
Variation in topography and difference in reflectivity. Yes, it is the correct answer. Only difference in reflectivities of the areas. No, it is not the correct answer. Difference in reflectivity is of area, but only topography. Here it is given, so that is not correct. Only topography Here it is also given, that is also not correct. And variation of thickness, thickness has nothing to do if we are going for a reflected microscopy. Thickness has something to do with when we are talking about the transmission mode. Okay, so thickness has nothing to do, so that means A is the correct answer. Okay.
I have a small query. Can you please see that?
Yeah, yeah.
Now, see, if you talk about the color etching, okay, in color etching, if you see, then they are in color etching, this reflectivity areas also matters, or topography also matters.
Sorry, I
If you see the samples under microscope
yes,
for color etching, or the color microscope, if you do the different color etching, another technique is there. Different etch and you can
yes,
see, and
yes,
different phase, different color you can see.
yes,
Correct.
yes.
In that scenario, you see BC also there is a difference is there. It also only topography also sometimes matter. Okay, only reflectivity also matter. Her topography is not there, then reflectivity also matters.
Yeah, but yes, but you are talking about a specific case. In that case also, what happens when you are talking here, the options is contrast in reflected microscopy. So you are talking about the etching in a specific applications, right? So in that case, when you are talking about talking in a specific application, in that case you might even in a only topographical, let's say there are topographical different topographical features are there in an object. But if you are not in some place you are getting light, and in from some place you will not be, you are not able to get the light cannot be reflected, then also you will not be able to get the contrast, right? So that application where you are saying that the color etching happen, or then you are implying a particular application, right? So
Okay.
so here I am talking in a contrast in reflective microscopy. We are not going to a specific application. Generally the contrast in reflected microscopy is a combination of, because how much topographical features are there in your object, and how much your object is able to reflect the light which is impinging on it from different areas. So it is the combination of the variations in topography as well as the differences in reflectivity. Does that clear the query?
Yes, yes.
Okay. So here it is a numerical question. If a graticule is observed under 10x lens of a microscope, so that the diameter of the field of view is from 150 micron to 450 micron on the graticule, what is the width of one lamella when it takes 15 lamellas to fill the field of view when viewed under 50x lens? So we will see this question. So here one thing is given as field of view. So field of view I have told as field of view index, if you remember, that is known as S, right? So that field of view is from 150 micron to 450 micron on the graticule. It has changed, right, when we are using a 10x lens. And so this field of view, if I am talking about field of view, is inversely proportional to the magnification here. Okay, that means when I am seeing an object, let's say here, when I am seeing an object in 1x magnification, let's say, then total I am able to see this entire rectangle. But when I am going for 10x magnification, then I might not be able to see the entire rectangle. Then in that case what I will be able to see the partial rectangle, right? And if I am increasing my magnification to, let's say, 20x, then I will get distinct small features in my object, but I will not be able to see, let's say this is A, B, C and D, this is a rectangle. I will not be able to see the complete rectangle. In that case I might be able to see, let's say, E, F, G and H. I'll be able to see this much, but with distinct features, small distinct features which I might not be able to see in 1x magnification. So that is what the field of view represents. So here the question is, if I am seeing my field of view changes from 150 micron to 450 micron, that means how much my field of view, if I'm using this magnification, my field of view is changing from 450 to 150. That means I am able to see 300 micron if I am changing my magnification to 10x, right? So in 10x magnification I am able to see 300 micron 300 micron field of view. So it is asking how much field of view I will be able to see using 50x lens. So 50x, so here it is 5. If I am increasing my magnification by 5, then my field of view will also be decreased by 5. That means if I am using a 10x magnification and I am able to see a 300 micron field of view, if I am using a higher magnification 50x, then I will be able to see 60 micron field of view, right? And if my total, so using a 50x magnification I am able to see a 60 micron field of view, but I might not necessarily might not use one lamella, or so it has asked that when it takes 15 lamella, how much you to see this 60 micron field of view, I might not necessarily use one lamella. I might use different sets of combination of lamella, or you can say a small so what is the width of the lamella? Yeah, I might not necessarily use one lamella to view this complete 60 micron field of view. I have to use, it has asked 50 lamella. So total field of view, if you are talking about, this is 60 micron. I need it to see it in 50x magnification. So for 15 lamella I am getting 60 micron field of view. If I am talking about one lamella, (60 by 15 is equal to 4 micrometer). Okay, so that means D will be the answer. Okay, so the sixth question, when the aperture, when the aperture is made smaller, which one of the following is correct? The depth of field and contrast increases, and the resolution decreases, the brightness increases. This is the statement 3. Statement 2 is the resolution decreases. So option is 1A is 1 only, option B is 1 and 2, option C is both 2 and 3, and then option D is all 1, 2 and 3. So can anyone answer?
B, sir.
Yeah, so the correct option is option B. Why? Because the job of aperture is to limit the light accordingly, whether we want all lights to fall on our sample or whether we want a portion of the light to fall on our sample. So when generally the aperture, what does it do? It limits the light, the total light, to fall on our sample. So that means the brightness, when we are not using the total light to illuminate our object, then the brightness will decrease, it will not increase. So statement 3 is wrong. And the resolution decreases. Why? Because we are limiting the amount of light to be fallen on our object. So that is why the resolution also decreases. Okay, and the depth of field and contrast increases. Why contrast increases? Because we are allowing a very thin section of light to be put on our sample, to be put on our object. So that is why, so we are illuminating a very small portion of our object. That is why the contrast will increase. Okay, and so that is why the statement 1 and the statement 2, they are correct. Okay, so when increasing the magnification, so question number 7 is, when increasing the magnification on the microscope, which of the following occurs? The depth of field increases, the resolution limit decreases, the visible area decreases, and the last option is the contrast increases.
C.
When increasing the magnification, which of the following
C
occurs?
is the answer.
The depth,
C.
the visible area, yes, that is the correct answer. When the increasing the magnification we are increasing means the visible area decreases. It has nothing to do with the depth of the resolution limit, because that depends on the wavelength of our incident beam. The contrast depends on the aperture that we are putting in our optical system, and depth of field formula is n lambda divided by numerical aperture square. So the magnification will be only the visible area decreases. Okay, yeah, so this is our next question. An object of height 2 centimeter is placed perpendicular to the principal axis of a convex lens of a focal length 15 centimeter. Find the size of the image if the object is at a distance of 12 centimeter from the lens. Okay, so find the size of the image. So the here we will put the thin lens equation. So what is the thin lens equation? Here they have given the object height is object height is 2 centimeter. So the principal axis of convex focal length. So here if we are putting the thin lens equation, means focal length they have given is f is equal to 15 centimeter, and then what they have given, the object distance, that means they have given the u distance, that means 12 centimeter. If I am talking about thin lens equation, then 1 by f is equal to 1 by u plus 1 by v. So in that case, so 1 by 15 is equal to 1 by u is 12 minus 1 by v, plus 1 by v. So that will give me 1 by v is equal to 1 by 15 minus 1 by 12, right? So this will give me 64 minus 5 minus 1 by 60, right? And v is equal to minus 60. Okay, so v minus 60 means what? That object and image they are formed on the opposite side of the lens. So that means v is equal to 60. So the distance of the image from the object from my lens is equal to 60 centimeter. So here if I am talking in terms of magnification is v by u. If I am taking only the distance, that means 60 divided by this is 60 divided by 12. 12 is my u, that means the object distance. So it will give me is 5, right? So magnification is 5. Magnification 5 means my object height was 2 centimeter, right? And magnification I am getting 5. That means my image height will be, so object image height will be magnification into object height. So that means 2 into 5 is equal to 10 centimeter. So option A will be correct. Okay, so question number 9, which part of a microscope is used to support the slide containing the specimen? This is the easiest question. So the answer will be, anyone?
D, sir.
D, yes. So the answer will be, so in specimen stage we used to keep our sample. So here stage is the answer, but we also will see a little what does the eyepiece do. Eyepiece increases the means magnification to a particular limit, which is coming magnification of the image which is found by the objective lens, and objective lens is its job is to focus to collect all the beams which are coming after interaction with the material, and condenser is to focus the beam which is coming from the illuminator or our illuminating system onto the sample. So these are the job of condenser, objective lens and eyepiece. So that is stage is the only part where we are keeping our sample. So here another thing, comet tail effect is noticed after which stage of the specimen preparation. So this comet tail effect,
Cloth polishing, you can say.
oh yes, so cloth polishing is the correct answer, because grinding, when we are doing the grinding, so scratches will be coming, right? Like this, scratches will be coming in the grinding. So grinding is not the correct answer. Then etching, when we are doing the etching means we are revealing the microstructure. It does not, whatever it is there in our sample, it is just we are just revealing it. So it is not giving any kind of effect. And mounting means we are holding our sample. So that means the cloth polishing is the polishing. That means when we are doing polishing with colloidal silica or polishing with alumina for finer polishing, or cloth polishing is done when we are using diamond slurry. In diamond slurry which is also used by using aerosol spray. So diamond slurry of 3 different categories we have seen in the videos how the specimen is prepared. So that is how in that stage comet tail effect is used. Then there is another question, crystals of different orientation are etched at different rates, and this results in can anyone answer what will be the, so this is a question related to the etching. Etching is the process which we do after coarse polishing. Then after coarse polishing we do the fine polishing, then we do the cloth polishing, and then finally we do the etching. So etching is the process where we want to see the different where we want our specimen to reveal its microstructure to the optical system. So this is the process where we see change in crystal orientation. The B answer is not correct, because etching does not change the crystal orientation. It just reveals the microstructure. Then elongation of grains, no, elongation of grains happens through a different process. Either it is chemically or thermally, when we keep the material for a longer period of time at high temperature, elongation. And when we apply some sort of load to the material, and then the resolution change, no, this is also not correct answer. So the correct answer is contrast change, okay, due to grain boundaries. So grain boundary, we can see the difference between grain boundary, we can see the contrast between grain boundary and our grains. So that is where this process of etching comes into place, right? And yeah, the next question is, there are two, three more questions, so we'll go through them quickly. So the next question is, what is the useful magnification of a microscope if the numerical aperture of the objective lens is 0.9? It is associated with our first lecture. So useful magnification is generally given by, if you remember, useful magnification, there is a total magnification and there is a useful magnification. So that useful magnification is given by 500 to 1000 times objective so 500 times to 1000 times the numerical aperture of objective. Okay, here I forgot the numerical aperture. So the 500 to 1000 times the magnification received from the numerical aperture of the objective lens is the useful magnification. So the numerical the magnification we receive from the numerical aperture of the objective lens through the numerical aperture of the objective lens is the total magnification is not is the total magnification if the eyepiece is not there. If the eyepiece is there, we still have to multiply that thing. But considering that currently that the eyepiece is not there, so the useful magnification will be the 500 to 1000 times numerical aperture of the objective lens. That means if we are putting so the numerical aperture of the objective lens is 0.9, 500 to 1000. If we are putting, then that value will give us 500 into 0.9, 450, 1000 to 900. So the option of C is correct. So this concept of useful magnification comes with, if you remember, the empty magnification, where I have shown you one image of 1x, 2x, 10x and 30x magnification, where we are only zooming the feature but not getting, we are not able to distinguish between two different points, right? And yeah, so the next question is, the three main etching techniques employed in the specimen preparation in optical microscopy are swab technique, immersion technique and electrolytic technique. Which among them are done manually? So can anyone answer this one? So there are three different techniques: swab, immersion and electrolytic etching technique, out of which among them these are done manually.
Sorry, swab only, swab.
C is necessary.
Of both, 1 and 2.
Yes.
If you see.
1 and 2.
Swab
C
and
basic.
swab and immersion. So both
Yeah.
are done manually, and electrolytic polishing is done automatic. And this, yeah. So sorry, etching, electrolytic etching, not polishing. So the correct answer will be 1 and 2. So this is 1. Okay. So I have not given the number. This is 1. Okay. This is 2, and this is 3. Okay. And yeah, so this is the last question. In fluorescence microscopy, the dichroic mirror acts as a band pass filter, whether it's true or false.
True, sir.
The dichroic mirror,
A.
no. The option would be false. There is a difference between band pass filter. So here, the mirror in fluorescent microscopy, what does it do? It is sorry, it is used as a long pass filter, not as a band pass filter. So the difference between band pass filter and the long pass filter is, in band pass filter we use the light of specific wavelength. That means this wavelength only we will allow. This is the band. That means the wavelength band is defined. No matter, so this is, if I am talking the wavelength, so this is what called band pass filter. But for in fluorescent microscopy, I use a long pass filter. That means so let's say this is my this thing, and this is lambda 1, and if my wavelength are increasing, I can design this, I have to design this dichloric mirror such that all the spectrum which are coming after this thing, right, they all will be allowed. Okay, so in that session, in that way, they all will be allowed to transmit. Okay, in that way. So in fluorescent microscopy, the dichloric mirror is used as a long pass filter instead of a band pass filter. So the difference, fundamental difference between a band pass and the long pass is, band pass only allows a certain wavelength, neither left to this nor neither left to this nor right to this one. Only in this region only in this region it will allow. But while a long pass filter, there is only one defined wavelength is there. After that, all these wavelengths are allowed to transmit. Okay, so that is the difference between a long pass and a band pass filter. Okay, so that was the last question. Okay, time. Okay, yeah, so that ends our session. Actually, thank you. I think we have well past the time. Uh, yeah, so if you have any queries or anything, you can ask, or you can also email, or you
I
can,
just only one query, that useful magnification,
yeah,
that you're doing 400 to
450 to 900.
900.
Yes.
This is objective lens multiplied by
Numerical aperture of the objective lens multiplied by 500 to 1000. So the limit is 500 to 1000 times numerical aperture of objective lens. That is the useful magnification.
there is the 500 to 1000 this range. Any logic behind that? Anything?
Yes, yes. There was a graph. If you remember, I have shown it in the first tutorial.
Okay.
So in that graph, like just few I just okay. So I will share that PDF with you again if you want. So in that graph actually we take a specific band, specific magnification. There is a mm, so in that, between that specific magnification only we will be able to use we will be able to view the image, and beyond that we are not able to use the image, because beyond that the criteria for the empty magnification takes place. So that is why the 500 to 1000, that range is defined for a useful magnification.
That is what with objective lens,
For
correct?
the objective lens, yes, because objective lens is the lens which collects all the light, whether it's diffraction, whether it's reflection or transmission. That is the lens which collects all the light from the specimen. So that is why the objective lens, the criteria for the useful magnification of the objective lens is the useful magnification is associated with the objective lens.
See, if you see the normal microscope,
Yes.
objective lens having the magnification of, that 5x,
Yes. Yes.
it has a 10x, then it is a 20x,
Yes.
correct?
Yes. Yes.
Like it increases.
Yes.
Yeah, even it is lower than that also is there nowadays, correct?
Yes. Yes.
1.125 also is there, what we are having. I just have a understanding if you go lower level also,
Hmm.
that how their graph, sorry I could not recollect that particular thing. How that also falling, that is it that falling that particular useful magnification or not?
Yeah, yes.
See, microscope today we can see that 12.5 microscope.
Yes. Yes.
How that is there? 1.25x magnification also we are using nowadays.
1 point, yes, 1.25 also we are using. So it's not like a, the x, you can imagine in this term. So the useful magnification area, if I can say that, let's say x axis you take some numbers, let's say 1 to 10, and the y axis you take some numbers, let's say from 1 to 10, then the useful magnification area is diagonally, like y is equal to x if you take, so it is diagonally. Let's say the x starts from 3 value, similarly y starts from 3 value. So it is going in the in that direction. So it is an area in between that thing, you will get the magnification.
No, that is okay. I understand. See, today, if you see the, if you take the, like, oil structure, if you want to see, if you do the oil, there's the area is very high, correct? In that cases, often your objective lens minimum level people are using today,
Yes. Yes.
correct?
Yes.
Just to have the better clarity that entire view how they are. And only my point is that how that is, I just could not try to correlate that theory versus actual, how it is fitting. Next class also you can explain me, no issue today.
Okay.
Is
Yeah,
our
I'll.
time.
Yeah, I will also look into that, because currently what seeing, yeah, I'm seeing is that how useful magnification is used. Okay, I'll also check and come back to you in the next class. Like you are asking, let's say in today we are using very low magnification also. Then in
Yes,
that case,
because
in that case, if we are using the useful magnification, then it would further. Uh,
much below that 500 to 1000 which
yes,
you are,
yes. So
that's my point, that how theoretically and
practical.
practical both the things are adjusted.
Okay,
You
okay.
take your time, next class also
Okay, yes.
conveniently
I'll,
you
yeah,
can.
I'll look more into it, and next class I'll come back to it.
Yeah, thank you, thank you.
Yeah. Yes. So if any other query is there, you can ask, or yeah, we can leave. Wish you a happy weekend. See you in the next lecture.
Thank you.
Thank you, sir. Thank you.
Thank you.